Hello, I'm Dongwon Lee. I'm going to present towards identifying robustness of out-of-distribution score on variational autoencoder. Deep learning models have revolutionized numerous fields showcasing exceptional performance and tasks ranging from computer vision to natural language processing. However, their potential is hindered by a critical challenge, their susceptibility to OOD data in real-world scenarios. Out of distribution is a distribution that does not belong to the distribution that the model has been trained on. As we deploy deep learning models in safety-critical applications like autonomous vehicles, the stakes are high. The vulnerability of these models to unexpected OOD data raises concerns. In the realm of autonomous vehicles, for instance, the ability to accurately detect OOD scenarios is paramount. Consider a situation where the model encounters an object it hasn't seen during training. A failure to distinguish such unknowns could result in accidents or malfunctions. To address this, our motivation is clear. We need effective OOD detection methods tailored for the unique challenge. This leads us to the likelihood regret score, a novel metric proposed. Likelihood regret, an out-of-the-distribution detection score for variational autoencoder. Here's a basic explanation of how likelihood regret is computed. At first, we train a generative model such as a VAE. We calculate the likelihood of out-of-distribution samples using the trained model, and then calculate the likelihood after optimizing the model for the sample. The likelihood regret is the difference between the likelihoods. We want to assess the ability of LR dealing with different versions of image which simulates real-world scenario. To evaluate the effectiveness of LR, we conducted experiments using diverse datasets. This includes transformed, corrupted, and adversarial examples. We generate adversarial dataset using fast gradient sign method, which is a well-known type of adversarial attack. We train VAEs on standard datasets like MNIST and Fashion MNIST. Moving on to our results, we observed the VAE's performance across various datasets. This is the histogram that depicts the distribution of score. The left picture is the histogram of likelihood regret computed by VAE trained on MNIST. When exposed to transformed MNIST samples, our VAE demonstrated a robust ability to detect these variations. However, a noteworthy observation is the widespread distribution of the Fashion MNIST, possibly stemming from the VAE's challenge in reconstructing the Fashion MNIST dataset. Conversely, in the right picture, which is the histogram of likelihood regret computed by VAE trained on Fashion MNIST, the LR score effectively distinguish OOD samples. An intriguing observation is the similarity in the LR distribution computed for EMNIST and EMNIST, suggesting that the VAE trained on Fashion MNIST has learned diverse features, including rotation. We also evaluate the likelihood regret score using AUC-ROC metric, which is a well-known metric for out-of-distribution tasks. We compared likelihood score and likelihood, which is also used for OOD tests. The table shows the AUC-ROC computed by VAE trained on MNIST. The AUC-ROC for both scores are high for OOD samples. However, their performance diminishes with corrupted samples. This may result from the vulnerability of VAE trained on clear image facing corrupted image. As we delve into the insights gained from our experience, we recognize the importance of LR in enhancing the robustness of deep learning models. The implications of our work extend beyond experimental setups. It has the potential to impact real-world applications, especially those demanding high levels of reliability and safety. Thank you.